Dear participants of the conference, your attention is presented a variant of controlling the heat supply system of buildings and structures using mathematical analysis methods. The authors of the study are Aleksey Burtsev, Milena Krivtsova, Maria Murzina, Scientific Staff Department of Infrastructure Energy Systems, Southwest State University. One of the important problems of our time in the general list of technical tasks includes the improvement of resource-saving technologies while simultaneously ensuring environmental safety. Practice shows that when implementing these issues, automatic control systems in hot water supply and heating systems of buildings and structures have a special advantage, allowing to reduce thermal energy consumption in the range of 10.30%. From operating experience, when introducing the mentioned technology, an open heat supply system, dependently connected by a supply line to the heating networks, proved to be the most optimal. Fig. 1. The proposed heat distribution option is preferred over the independent one, due to the absence of the need to use heat exchange equipment, groups of makeup pumps and an expansion tank. The proposed heat distribution option is preferred over the independent one, due to the absence of the need to use heat exchange equipment, groups of makeup pumps and an expansion tank. It should be noted that this approach to heating control contains some danger for the heat supply system in the event of a water hammer in the return pipeline. If an emergency value is reached, this can lead to failure of a number of thermal power equipment. In reality, the majority of modern operating facilities such as nuclear power plants, thermal power plants, and hydroelectric power plants protect main heat pipelines from emergency situations. Note that the indicated temperature values are nominal, equals 80.150 degrees Celsius, equals 20.22 degrees Celsius, equals 60.70 degrees S. The outside air temperature is determined in accordance with SP 131, 13330. 2020 Building Climatology. The dynamics of heat supply require the use of a hot coolant, the temperature of which must have a nominal value. It flows from the heat main to the control valve V1, which controls the process of regulating the heat supply to the heat load R, to maintain the standard nominal temperature in it, buildings and structures. The process of maintaining the temperature is controlled by feeding the ARBA circuit with hot coolant at point A. Circulation is provided using pump N, which mixes the hot coolant in the required volume. As a result of heat transfer, a cooled coolant with a nominal temperature enters the return pipeline, 3 to 9. In scientific works, 3 to 15, the proposed approach makes it possible to describe the main features of the heat transfer process by certain functions, including coordinates and time. We can then present our model as a series of solutions for various problems of heat convection caused by certain factors. To represent the heat supply process in the form of a mathematical model, it is necessary to take into account the following parameters. Geometric characteristics of the pipe section, external D1 and internal D2 diameter, m. Contour length L, m. Physical properties of the medium, heat capacity C, J per kilogram degree C. Thermal conductivity lambda, W per meter degree C. Density ρ, kilogram per meter 3. Intensity of heat losses, volume heat density QV, W per cubic meter. Heat flow Q, W per meter 3. Heat exchange conditions at the boundaries of the site. A mathematical model of the heat and mass transfer process can be presented in the form of a system of Navier-Stokes equations to describe the movement of the medium omega over time tau and temperature T in the orthogonal coordinate system x, y, z, as well as energy equations to determine the temperature field and boundary conditions taking into account heat transfer on the walls pipes. As a result of solving this system of equations, it is possible to determine the temperature distribution inside the pipe section, as well as heat loss in each section. This will optimize the heat supply process, minimize heat loss and ensure the required temperature in the room. In passing, we note that the abscissa axis contains the origin of coordinates and is directed along the axis of the pipe. At the same time, the ordinate and applicate axes originate from the specified origin in a plane normal to the abscissa axis, pipe axis. 4. Assuming that the temperature parameters in the dependent system change over time, let us consider the unsteady operating mode of the ARBA circuit. In this case, the movement of working heat occurs along the abscissa axis, and in an arbitrary section its consumption G1 and temperature T1 change over time. That is, the following relations are valid. Partial differential T, partial differential tau does not equal 0 omega underscore x equals omega underscore y equals omega underscore z equals 0, delta T equals 0. Considering that in most cases the value QV is practically absent, a one-dimensional function T equals f, tau, taking into account the time constant of the thermal load Tp and the amplification factor of the temperature pressure in the heat supply system K. which is a constant proportional to the ratio of temperatures in the supply and return pipelines T2, T1, and depending on the geometric and physical properties of the thermal load, can be written as. Let us consider two possible models of heat supply control, respectively, based on expressions 21 and 23. A. Single parameter control. As a control parameter when regulating the heat load, we select the ambient temperature, outside air. Suppose T_x changed by an amount of delta T_x, then we get its value equal to T_x plus delta T_x. Assuming that K_n, F, T_int, eta, S_p, G_n, T_1, T_2 is not subject to change, it is sufficient to change the value of G_1 by an amount of delta G_1 so as to maintain the constancy of T_int. As a result we get B. Two-parameter control. In this case, the control parameters are the ambient temperature, outside air, T_x and air temperature in heated room T_int while providing thermal load R. Let us consider the case when not only changes T_x by the amount delta T_x, but also T_int by the amount delta T_int in relation 27. In this case the expression delta G_1 subject to constant values K_p, F, T_int, eta, S_p, G_n, T_1, T_2, will take the form, Fig. 4. During the study using mathematical analysis methods, the following results were obtained. 1. Working formula for controlling the process of heat supply to buildings and structures for a dependent heating system. 2. An analysis and study of the effectiveness of the found formula was carried out in comparison with different heat supply methods. 3. The influence of the transition process is taken into account. 4. The corresponding smart home scheme has been synthesized. 5. A comparative study of the results obtained was carried out. An increase of 84% was established with savings in thermal energy costs. Thanks for your attention.